Hello and welcome to TI Precision Labs. TI's Precision Labs video program is a comprehensive online curriculum for engineers. This video covers the basic questions you may have about isolated inputs. More videos and topics can be found by going to ti.com/Precision Labs. What are isolated digital inputs? In previous videos, we've discussed galvanic isolation and the inner workings of digital isolators. In this video, we will introduce a different isolation device, the function of isolated digital input. Unlike the standard pinout of more commonly seen digital isolators, isolated digital inputs act as digital receivers with wide input ranges and a modified internal architecture that makes them uniquely suited for digital input module designs. This Precision Labs video will answer the following questions. What is an isolated digital input? How do isolated digital inputs work? Are digital isolators and isolated inputs different? What is the difference between an isolated input and an optocoupler? And what are the typical uses of an isolated digital input? In the previous Precision Lab about digital isolators, we shared a diagram of a typical digital isolator use case and highlighted that digital isolators sit between MCUs, FPGAs, and ADCs to prevent exposure to the potential risk of a high voltage event. The signal range for digital isolators falls into the TTL and CMOS logic ranges of roughly 3.3 to 5.5 volts. The isolated digital input is a little different. Isolated digital inputs serve the function of providing galvanic isolation from a sensor input or other input type to a logic output, and instead of functioning in the signal path between two digital components like the digital isolator, the digital input is actually designed to receive a wide range of input signals from field-side inputs, like the one shown here in a programmable logic controller design. The digital input interfaces with field-side input signals and sensors in the case of the digital input module, and has an input range of 5 to 60 volts, or sometimes even greater. Let's compare the internal structure of the digital isolator and an isolated digital input and an optocoupler to get a better understanding of how these devices function. There are three main structural differences to highlight between an isolated input and a digital isolator. Recall from the previous Precision Lab that a digital isolator requires two separate supply and ground pins, and that the digital isolator takes a low voltage logic input signal, modulates the signal, passes it through the isolation barrier, and then demodulates the signal to recreate the digital input at the output pin. An isolated digital input device commonly receives 5 volt to 60 volt digital input signals and provides an isolated digital output. Unlike the digital isolator, the digital input signal can also serve as the primary or field side power supply, keeping the device powered as long as the input signal is present. Internal voltage comparators connected to the sense pins determine the input voltage transition thresholds, and a field side ground, FGND, is required to reference the circuit to the same common mode as the input. The voltage input threshold is related to the input supply and can be programmed by the user with external resistors. Once the input signal meets the user program threshold value, the remainder of the isolated input device acts very similarly to the digital isolator. The input is modulated to pass through the isolation barrier, demodulated to a low voltage digital output, and output buffers on the control side are typically capable of providing enough current to drive status LEDs, which is a common need for digital inputs in PLC designs. The EN or enable pin is used to enable the output buffers, and a low state on the EN pin puts the output buffers in a high impedance state, while a separate supply and ground are required on the secondary side. Input range, pinouts, programmability, and internal functions are unique from one device to the next, and selecting the best isolated input for your design will require a close look at the feature set that best serves the need of your design. How are isolated digital inputs and optocouplers different? Isolated digital inputs and optocouplers vary in many aspects, including isolation technology, device pinout, and functionality. But do these differences matter in their function as isolated inputs? With respect to design of digital input modules, there are some differences to note. Long-term reliability and significantly different fit rates are some of the differences between the two device functions, but more commonly known differences include response times and function integration. Let's take a look at three of the most common use cases of isolated digital inputs to see how these performance differences are reflected in digital input module designs. Digital inputs in motor control. The control module in an AC motor drive is responsible for the signal processing and overall control algorithms for the motor drive system, based on inputs from the position feedback module or other monitoring functions in the form of analog inputs and digital inputs. These digital inputs are usually 24-volt signals from field sensors and switches communicating emergency stop signals such as safe torque off or information about the motor's operation such as speed and position. A typical AC motor drive is shown here. The digital I/O interface represents digital input feedback functions used to isolate feedback signals from safety and fault monitoring throughout the system, position, phase, and power signals. An added benefit of isolating the digital inputs from the control module is the prevention of ground potential differences from causing communication errors. In motor control, digital inputs are often used to provide a PWM pulse chain, which helps to control motor speed. Alternatively, with control algorithms, digital signal inputs make any necessary adjustments to the power stage in order to achieve a target output. In these cases, the speed of an optocoupler can often present a challenge due to limiting data rate. Propagation delay for an opto ranges in the microseconds, and a delay in response time can be critical in the use case of monitoring position feedback, which could risk instability and control of the feedback loop. Capacitive-based isolated digital inputs use high-speed technology which increases data rates and reduces propagation delay to nanoseconds for faster response time for critical feedback signals. The integrated functions of isolated inputs also help to address the challenges of both the size of the digital I/O interface and the need for improved noise immunity. This circuit shows a common optocoupler solution for an isolated digital input that uses several discrete components to implement a current limit and controlled voltage thresholds. Using this complex solution typically requires a Schmitt trigger buffer after the optocoupler to provide hysteresis for noise immunity. The additional hysteresis is required to account for part-to-part skew, which is common to optocouplers, in order to prevent noise signals from triggering an output error. Isolated digital inputs include hysteresis circuitry that is typically set by an external resistor, which ensures a more accurate window of input detection. Looking at the use of digital inputs in programmable logic control, the function of the isolated input in design is very similar to that of the motor control use, with slightly different priorities. The IEC 61131-2 standard for programmable logic controllers specifies 3 different types of digital input receivers, types 1, 2, and 3, with specific input voltage and input current relationships. As an example, implementations for a type 3 should draw close to 2 milliamps as possible on the on state, and have voltage transition thresholds between 5 and 11 volts, as shown here in the voltage versus current diagram. To achieve this operating behavior for the input of a Type 3 PLC digital input with an optocoupler, a typical circuit would look something like the following, and would still require discrete implementation of a current limit function needed to limit the current to below 15 milliamps. The implementation would require between 9 to 15 additional components, plus the use of a Schmitt trigger buffer to introduce that hysteresis to manage input voltage and thresholds for noise. Digital inputs and power distribution. 110 volt AC and 240 volt AC are popular line voltages for domestic and industrial use. 110 volts and 220 volts DC batteries are used as auxiliary power supplies in power distribution and power station automation. The detection of the absence or presence of these line voltage and battery voltages and their exact levels or the status of relays that connect to them is an important function in power distribution systems for industrial automation and protection relays, among others. Traditionally, AC voltage detection circuits could be used building optocouplers, as shown here. A full bridge rectifier would rectify the AC voltage into DC, and a Zener diode ensures that the optocoupler receives input current only beyond a certain voltage, which roughly creates a threshold control. The addition of the 2 resistors of R1 and R2 provides some voltage control while limiting the input current. This same circuit could be used without the bridge rectifier for DC detection as well. So why would this circuit be designed any differently today? CTR ratio is the ratio of output current to the input current at the internal LED of the optocoupler, or gain from the primary to the secondary side. CTR degradation is a common occurrence with optocouplers due to the reduction of LED efficiency over time. When CTR of an optocoupler decreases, higher and higher currents are required to maintain target operating voltage levels, which results in higher and higher power consumption and higher board temperatures. Isolated digital inputs offer a solution to this issue with the use of capacitive architecture, which does not have the aging issues of CTR or LED efficiency. Because the isolated digital input offers programmable integrated current limits and threshold voltages, input current is held constant, resulting in lower power dissipation and longer operating lifetimes without the negative effects of LED aging. We've discussed that isolated digital inputs provide galvanic isolation from a sensor input or other input type to a logic output. Isolated inputs directly sense an input signal from 0 to 60 volts or higher, and they can be used instead of optocouplers and digital input circuits with integrated functions that offer higher speed, smaller profiles, and improved lifetime and thermal performance. Thank you for watching. Please try the online quiz. Question 1. What are the three primary differences between digital isolators and isolated digital inputs? Input range. Input range for digital isolators is typically aligned with the TTL or CMOS logic inputs of 3 to 5 volts. For isolated digital inputs, the range can be much wider, between 5 to 60 volts or beyond. Primary and secondary power supply requirements. We talked about how digital isolators require both primary and secondary isolated power supplies, whereas the isolated digital input can use field side input power instead of a primary power supply. Integrated functions. Isolated digital inputs include integrated functions like hysteresis and current limit, and the feature set should be thoroughly investigated before making your isolated digital input selection. Quiz question number 2. Can isolated digital inputs be used instead of optocouplers in digital input design? Yes, isolated digital inputs are not typically pin-to-pin with optocouplers, but they can replace optocoupler-based circuits with fewer components and longer lifetime operation. Question number 3. True or false? Since power can come from the output pin, for the isolated digital input shown, VCC1 can be left disconnected during operation. False. Field side digital inputs can be used as a power supply to keep the device powered for the primary side as long as the input signal is present. However, the secondary side or output requires power to operate normally, so VCC1, shown here, must be connected. This concludes the Precision Labs What is an Isolated Digital Input? Thank you for watching. You can browse more topics for Precision Labs at www.ti.com/Precision Labs.